Hello and welcome to Homework 1, Part 1. In this part of the homework, in Part 1, we are going to look at an example here and where we are looking at a conical tank. So essentially a tank that is slanted on the sides and gets smaller, has a smaller cross-sectional area on the bottom when compared to the top of the tank. And what we have here is some Q in, some fluid flowing into the tank. And at the bottom here, we have a small circle or just an opening, and we have the fluid draining out of the tank, out of this hole. And what we are asked to do in part one is to derive an expression to see how the fluid height in the tank changes with time. And then in part two, what we're going to do is basically simulate this in Python to run the derivations that we have found here and basically plot them out and verify that what we have derived is correct. So if we want to derive an expression for the change of height with respect to time, what we can first look at is the change in volume with respect to time. So if we look at dv dt, we know that this is just simply a function of our flow rates. So we know this is equal to Q in minus Q out, and that makes sense. The change in volume will just simply be equal to the flow rates in minus out. Now, what we can look at next here is sort of an energy balance to the situation. So if we look at the fluid level at the top here, we know that there is potential energy of the fluid at the top. And what we're going to say is that this potential energy turns completely into kinetic energy at the bottom. And we can say this because what we're assuming here is that this hole at the bottom of the tank is much, much smaller in cross-sectional area when compared to the cross-sectional area of the top of the tank. So essentially assuming that there's negligible kinetic energy at our fluid level, or whatever the fluid level is at the top. So if we do this, we can set the potential energy equal to the kinetic energy, and we know that kinetic energy is v squared over 2, and that potential energy is gh. So what we can do here is then solve for v out, the velocity at the bottom of the tank. So if we solve for v here, v out is equal to the square root, because we'll be taking the square root of both sides, and we'll have 2gh. Okay, so now we have an expression for the velocity of the fluid leaving the tank. Now, what we can do after this is take a second look here at this volume. And what we can also say about the volume is that the volume is equal to the integral of the cross-sectional area, so AC, and then times the differential change in height. Now, if the height wasn't changing in this situation, so if we had some steady state process, we would just have the cross-sectional area times the height. However, we will, when we simulate this in part two, we will have the flow rates changing, and therefore the height will be changing. So we'll integrate this from 0 to some height, and then we can make this what I'll call a dummy variable of integration. So this is an expression for volume here. Let me put a VOL to not get confused with velocity out. So now what we can look at here, if we want to end up getting to change in height with respect to time, is this change in volume with respect to time. Now we know that change in volume with respect to time will also depend on the height, as well as the change in height with respect to time. Okay. So what we can go ahead and do is make a plot, and what I'm going to do is put the cross-sectional area AC as the dependent variable on the y-axis and height on the x-axis. And if we make a plot of this, what it will end up looking like is something along the lines of this. And we know that this makes sense because as we go up in height, our cross-sectional area will be changing, as it'll be pi r squared, which is a quadratic. So we'll have some sort of parabola looking shape here on this plot. And what we can also do as we look at this plot is if we look at, say we were at some height over here, if we look at this area under the curve here, Well, we know that this is the volume because we know that it's the integral of the cross-sectional area times the differential change in height. So what is the differential change in volume with respect to height? What is that? Well, it's the cross-sectional area right here. So what we can say here is that this term is equal to the cross-sectional area. So what we can do here is combine some of the ideas that we have expressed, and what we have is our cross-sectional area times dH dt. This is equal to our flow rate in minus our flow rate out. And we can simplify this a little bit further because we know we have the velocity of the fluid going out. So what we can do is take our velocity here and multiply it by the cross-sectional area of the hull here. And notice that this is not the cross-sectional area of the tank, but of the hull at the bottom, because we're talking about the velocity going out. So simplifying this down, we'll have the cross-sectional area times the differential change in height is equal to Qn minus, we'll have the square root of 2gh, and then multiplied by the cross-sectional area of the hull, AH. So this, what we have derived here, essentially is some nonlinear ordinary differential equation. And what we can do here is, in the back half of this video, I'm going to go into Python and basically simulate this process here. And I believe what we're going to be doing is increasing the flow rate from an initial steady state and see how that impacts the height with respect to time as we increase that flow rate. So what we can do here is we can isolate our differential change in height with respect to time, and then we can go ahead and plot that as well, just to give us some sort of visualization to verify that what we have derived makes sense. So let's go ahead and head into Python. Okay, so we have our system set up here in Python. Essentially what we have here is the conical tank, and we're going to say that this conical tank has been at steady state for some long period of time. And all we're going to do here is just manipulate the flow rate into the tank. So we're going to raise it by a factor of 20%, or just multiply the initial flow rate by 1.2. And what we want to see is how the height of the tank changes with that increase in flow rate over time. So what I've gone ahead and done here is imported some tools that we'll need to be able to solve our differential equation, as well as plot that to see our results over time. And in this second block of coding here, what I've done is brought in the givens that we have been given for this problem. The first thing here is that we know that the hole at the bottom of the tank that the fluid is draining out of is 0.01. That's the size of it. We have G, our gravitational constant, 9.81. We have our initial flow rate into the tank, which is 0.1 cubic meters per second. And then we have basically some dimensions here of our conical tank. We have the radius of the bottom of the tank at 1 meter, the radius of the top of the tank at 5 meters, and the total height of the tank as 8 meters. And then this T end here, I named it Tn because I'm going to use it as our time in our plot. But essentially what we want to look at is we want to see how this change occurs over a period of 50,000 seconds. So what I'm going to do first here is that you'll notice for our initial steady state, what we are given is our flow rate into the tank. Now we could be given the initial height and we could calculate the initial flow rate from that. But because we don't have the initial height, I'm going to go ahead and calculate it here first. And to calculate this, what we're going to do is use the initial flow rate. If you go back to the derivation that we did, it'll be the initial flow rate divided by the cross-sectional area of the hole at the bottom. And this is going to be all squared. And then I believe we're going to divide this by 2 times G. So 2G. So that is the initial height of our tank. So we can already calculate that right off the bat. So I'm going to press Shift Enter here, and what I'm going to do is define a function so that we can solve our initial value problem using solve IVP. So I'm going to find a function. I'm going to name it right hand side, because we're going to bring everything over to the right hand side and set that all equal to 0 to be able to solve the differential equation. So first is our independent variable time, and then we have a vector of our dependent variables that it wants to take in. However, we only have one differential equation here. I'm just going to call that h for height. And what we want to return out of this is, let's see here, we're going to have our initial flow rate, or not our initial flow rate, but Q in minus AH. And I believe this is multiplied by 2GH to the 1/2 actually. So go multiplied by 2 times G times H. That all raised to the 1/2. Put a parentheses there, and this entire thing is divided by the cross-sectional area of the hole here. Or not the hole, the cross-sectional area of the height of the fluid. Okay, so two things we don't know here. One is our Qn, but like I said, what we do know is our initial flow rate in, and that is 0.1 cubic meters per second. And what we're going to do in this situation is we're going to raise that flow rate by 20%. So I'm going to multiply our initial flow rate by 20%. So we'll do 1.2 times Qn naught. And you'll notice here, let me press Shift Enter just to make sure that this runs, but you'll notice here that we don't know the cross-sectional area of the height of the fluid, AC. So what we can actually do here, because we are given R bottom, R top, and H total, is we can actually define a function to be able to calculate AC. So I have a picture here. I'm going to go ahead and pull this up. So what we can do here, because we are given values for both the radius of the top of the tank and the radius of the bottom of the tank, as well as the total height of the tank, what we can do is plot the radius on the y-axis and the height on the x-axis. And because we know that this relationship is linear, what we can do here is actually create a y equals mx plus b equation that can allow us to solve for r, the radius. And then what we can do from there is just simply plug r into pi r squared to get the cross-sectional area. So if we look here on the plot, we have r bottom here at some point on the y-axis. We have r top, the top of the tank's radius here up above this. And we also have here somewhere along the x-axis is the total height of the tank. So what we can do here is we can put r is equal to r top minus r bottom multiplied by, divided by h total, which is then multiplied by h, and then we would add the y-intercept of r bottom at the end. So we can have an expression for r, the radius. So let's go ahead here and define a function. So I'll call it conical tank cross-sectional area. So conical, did I spell it right? Yep, conical tank AC. And what we will be supplying here is H, R top, R bottom, and what's the last one here? R top, R bottom, and H total, right? And now we can go ahead and calculate R. So we'll calculate R is equal to R top, R top minus R bottom. So this will be multiplied by H and then divided by H total. And then we will add on R bottom as our y-intercept. And then what we'll do in this function is return that cross-sectional area AC. So we'll do np dot pi times r squared, and that will return us our cross-sectional area AC. So we'll go Shift Enter there. So now that we have everything that we need, what we can do is go ahead. Let me bring this up here. Just copy this, Control C, and set this equal to AC. Okay. And run this. And now what we can do is go ahead and set up to solve our initial value problem. So I'm going ahead and capture the result by setting this equal to res. So I'm going to unpack it already. This is equal to solve IVP. We're going to have the right hand side, our time stand, which is 0 to t end. Whoops. And then we are going to have our initial values, and I'm going to supply them as a one-dimensional array. Our initial height, so h naught, and then dense output is equal to true. Okay. Now what I'm going to do is I'm going to actually return this right-hand side as an array as well. NP array. Okay. Okay, so now what we can do is we can run this, make sure it runs here, and we can go ahead and plot this out. So we'll go ahead and make some plotting points. So I'll make a variable for tplot and linearly we'll space some points here. So np.lin space go 0 to t end and do 100 of them. And then we're going to set h equal to res and grab the solution, evaluate it at tplot, and then also take that one-dimensional array. And we can go ahead and make our plot. So I believe it's fig equals make subplot, and then we'll add a scatter plot. Why is it fig equal make subplot? Is it plural? It is plural. Fig dot add scatter. We'll have our x values be our tplot and y as the height to see that rise. And I'll go ahead and well, actually let's see how it looks. Oops. Oh, that's not right. Okay, so we can see it come to a steady state here. So we start here at some height, and over a period of time, I believe we have it running for 50,000 seconds. I can't remember if in the problem we're asked to do 5,000 or 50,000, but 5,000 it doesn't look like it's getting there yet. But if we do something like 50,000 seconds, we can definitely see it getting to that second steady state after increasing the flow rate by 20%. So that will do it for this part of the homework. Thank you.